We're going to start out this lecture looking at a reaction that has two different states of matter. So we will look at this as homogeneous versus heterogeneous reactions. And the one specifically we're going to look at in this example is having calcium carbonate solid decomposing. And when it decomposes, it forms some calcium oxide solid and some carbon dioxide gas. And when I look at what would be the equilibrium expression for this, products over reactants, two products, one reactant, what we will find is the concentration of carbon dioxide, and or you could write this simply as the pressure of carbon dioxide gas. Either one, different values, but either one would work for this. So concentration in moles per liter or ATMs of pressure. And of course, we showed earlier how we could transfer it back and forth between those two things. But the solids are not included in the equilibrium expression. And the reason they are not is because they're pure. You can't change the concentration of a pure substance. Same thing with liquid water, or water period, but liquid water. The concentration is 100%, so we don't show it in the expression. It doesn't change anything. So let me just kind of write this down here. Notice these solids are not in the expression. Meaning their values do not matter as long as they are present. So I'm not referring to concentration, I'm referring to how much, how many grams of these. So again, the concentration, 100%. I could have 1 gram or 1,000,000 grams, it doesn't matter. Same thing with calcium carbonate. It just has to be present, and that you will establish an equilibrium back and forth. Okay, let's do a little example-y kind of problem in looking at this. So we'll rewrite that expression up here at the top, and we will say calcium carbonate solid forming calcium oxide solid and carbon dioxide. And I'm pretty much just playing off what we were just looking at in the previous example. Actually, I just forgot something. There's some more notes I want to do, and we could talk about this right now, but it'll make more sense if we come back to this after I go through a few more bits of notes. So hold this thought. I'm going to leave some space in here up to right about there, and we'll come back to it. So it'll be better when we come back. So hold that thought. Predicting direction. And we can look at something, instead of K, we're going to use a Q value. So which way does a reaction shift for balance? So Q is whatever values we put into equilibrium expression. So for example, we have equilibrium and we have a number, right? That constant kind of shows the balance, but you could have any numbers of concentrations that you just happen to have lying around and you throw the system together. So if you have a Q, in other words, products over reactants, and you do the math as far as what's in there and you look at the exponential values, and you come up with a number which is greater than K, well, that tells you that either your numerator, products, are too large or your denominator is too small, the reactants. So if that is the case, in order to establish equilibrium, then the reactants must, I don't want to use the word must, I'll say moves to the left than reaction, I said reactants, excuse me. Reaction, it's like something doesn't make sense there. The reaction moves to the left to return to K, equilibrium. If Q is less than K, then the reaction moves to the right to balance K. And then, of course, if Q is equal to K, then you are at equilibrium. So, which of course would be really, really rare, that you have values that just happen to be exactly what you need to be at equilibrium. It's possible, not likely. All right, this is the tidbit of information that'll make that problem at the top a lot more easy. Okay. It is called Le Chatelier's principle. Le Chatelier's principle. And it's how and why a reaction shifts. So this also explains that problem in the very beginning in the homework packet that I said just take my word for it. Once we go through this, you'll be able to look at it and say, okay, that makes a little more sense, hopefully. If a system is disturbed, it will shift in a way to alleviate, and space there, sorry, alleviate the stress on the system. So let's look at a couple examples. If we increase a reactant the reaction shifts to the right. So again, think of it kind of like a teeter-totter. That's kind of how I should think of it. So it's balanced, however it happens to be. Again, it's not equal, but it is what it is. So you have some K value that goes to it. Maybe it's very heavily weighted on the right or the left. It doesn't matter. It's what it is. But if we increase the reactance, so however it was, this side falls because it's out of balance. The only way to bring it back into whatever balance it was is to shift some of that to the right to bring it back to whatever balance it was in. And we can look at this a lot of different ways, which we will continue to do here. If we take a reactant away, the reaction shifts to the left. So again, think of this like a teeter-totter. If I take some of the weight away, I take a reactant away, it bounces up. The right side becomes relatively heavier than the left. In order to bring back this balance, I have to take some of the products and shift them back to the left. Next one. If we add heat or thermal energy, the reaction moves opposite to the side energy is found, and this is very important, a new value for K is created. So remember, K is temperature dependent. So once you have a temperature, that K will never change. And you can do all these other things here as far as shifting right and left, back and forth, and you still will have the same K, even though you messed with the amount of reactants or products. But when you add heat, that is the only thing that will shift the reaction. In other words, that's why I always write the word energy in the balanced chemical equation. If you add energy, treat it like anything else in the equation. So for example, if energy was written over here and I added energy, I heated it up, it would shift to the left to rebalance. Treat it just like a thing in the equation. So write the word energy in, or a very specific value. All right, we're kind of running over here on time, so I'm going to stop here and we'll continue this in the next lecture.